Okay, today's topic is voltage division and current division rule. Before going to this voltage division and current rule, just we will recall the basic two circuit laws in circuit theory. One is Ohm's law and next one is Kirchhoff's law. And in Ohm's law it states that the voltage across a resistor is directly proportional to the current flowing through it at constant temperature. And this is the relationship for the resistance, where rho is the resistivity and it is given by R is rho L by A. Here resistance is directly proportional to the length of the conductor and inversely proportional to the area of cross section. And in this one, the Ohm's law it states that I equal to V by R, or directly we can call it as P equal to IR. Next one is Kirchhoff's law. Kirchhoff's law is two types. One is Kirchhoff's current law, next one is Kirchhoff's voltage law. Kirchhoff's current law it states that the algebraic sum of the current entering into a node is equal to sum of the current leaving the node. Here we can take a simple circuit which consists of single node, where it states that the sum of the current entering into the node is equal to sum of the current leaving the node. So here the entering currents are I1, I2 and I4, and the leaving currents are I3 and I5. So according to this Kirchhoff's current law, it can be given as I1 plus I2 plus I4 is equal to I3 plus I5. Next one is Kirchhoff's voltage law. It states that the algebraic sum of the voltages around any loop is equal to 0. So it is given by, we can take a simple series circuits. The sign convention here we can take in either clockwise direction or anti-clockwise direction. So here we will consider two resistances R1 and R2. They are connected in series. Let the voltage across this R1 is taken as V1 and voltage across R2 is taken as V2, and the applied voltage is V0, and the current flowing through these two resistors, since they are connected in series, the current will be constant. So the according to this, when we take clockwise direction, we can give it as minus V0 plus V1 plus V2 is equal to 0. By applying this Kirchhoff's voltage law, the relation will come like this: minus V0 plus V1 plus V2 is equal to 0. If you take the counterclockwise direction, it will be minus V2 minus V1 plus V0 equal to 0. If you do in either ways, the answer will be the same. So from this we can tell V0 is equal to V1 plus V2. Now we will consider a series resistors types. Again the same thing, the voltage across R1 is V1 and voltage across R2 is V2. Applied voltage is V0. According to Kirchhoff's voltage law, we know V0 is equal to V1 plus V2, and in turn V1 is equal to since they are connected in series, the current remains same. So V1 can be written as, according to Ohm's law, V1 is equal to I into R1 and V2 is equal to I into R2. So we can write V0 is equal to I into R1 plus R2. So from there, let us give Rs is the equivalent resistance for series resistors that we see in the last activity. When two resistances connected in series, the equivalent resistance will become R1 plus R2. So Rs equal to R1 plus R2. Now if you look at this circuit, here what happened means the current remains the same. So here the current remains the same for both R1 and R2, but what happens means here voltage gets divided. So here we are going to apply the voltage division rule. So now our aim is to find out this V1 and V2 in terms of V0. So for that we know I is equal to voltage, applied voltage divided by total resistance. So V0 divided by R1 plus R2. In similar way, V2 is equal to I into R2, but I is equal to V0 divided by R1 plus R2. So by substituting that, we will be getting V2 is equal to R2 divided by R1 plus R2 into V0. So here V2 is the voltage that is divided from V0. So again, in similar way, V1 can be given as R1 divided by R1 plus R2 into V0. Next one, we will see the parallel resistor circuits. Here, two resistors are connected in parallel. R1 and R2 are the two resistances. They are connected in parallel. So here, if you look at here, the current gets divided. By using our Kirchhoff's current law, we can see that this current I is split into I1 and I2. So by using Kirchhoff's current law, we can give it as I is equal to I1 plus I2. Again, by using Ohm's law, we know I1 is equal to voltage drop across this R1 divided by R1. Since they are connected in parallel, what happens? The voltage remains the same. So I1 is given by V divided by R1 and I2 is given by V divided by R2. So it is given as V into 1 by R1 plus 1 by R2. So here we are going to take the equivalent resistance between these two is taken as Rp. Then I is equal to V by Rp, where Rp is equal to 1 by R1 plus 1 by R2, or else simply we can write as R1 R2 divided by R1 plus R2. Now we'll get the expression for I1 and I2, where these I1 I2 are get divided. Right? So the expression for I1 and I2 is taken as, first V of t is equal to Rp. Rp is the equivalent resistance into I of t, where Rp is just now we have seen R1 R2 divided by R1 plus R2 into I of t. So I1 of t is given by V of t, where V of t is the voltage across R1. Both R1 and R2 having the same voltage V of t. I1 of t equal to V of t divided by R1, and this is given by R2 divided by R1 plus R2 into I of t. In similar way, for I of t, V of t divided by R2. V of t is equal to R1 R2 divided by R1 plus R2 into I of t. Then we substitute that, we will be getting I2 of t equal to R1 divided by R1 plus R2 into I of t. Now here what happened means, in current division rule, the resistance gets inversely proportional to the resistance, because if you take I1 of t, it comes in the numerator R2. In similar way, I2, the numerator part is R1. In the previous case, in voltage division rule, V1 is directly proportional to the own resistance. So V1 equal to R1 divided by R1 plus R2 into V0. So this is all about the voltage division rule and current division rule. Thank you.